Hey guys, this is Tommy. Today what I want to do is I want to take you through what's called the OSI model, but really what I would consider the level set mechanism that we use in order to establish a base level of knowledge, a set of terms and technologies that we use in computing in order to allow machines to communicate with one another. And so I want to kind of demystify that technology. It's called the OSI model, and talk to you a little bit about how it works in today's day and age and how we use it and things like that. So a lot of times this is something that will help you to understand how communication works and help you to understand why data addresses and cryptographic methods and things like that are so important when we're communicating digitally. So let's go ahead and take a look. So what I want to do first is I'm just going to open up Microsoft Paint, or just Paint here, and I'm going to paste in the OSI model. So here it is. By the way, if you're not familiar with this, it's the Open Systems Integration. That's what the OSI stands for. And it was created by actually the ISO, or the International Standards Organization. So the ISO created the OSI, and these 7 layers were actually created in 1977. Kind of unique, right? So we're almost 50 years into using this model, and what they decided to do is, up to this point, all these vendors had these dissimilar products that kind of did the same thing, and they wanted to make sure that they defined standards that would allow them to interoperate. And that's what this basically does. Open systems integration. We're interoperating and allowing for interoperation between systems. And so when you think about this, a lot of times people will talk about, please do not throw sausage pizza away, or all people seem to need data processing. That's how they remember that first word of each one of these layers. But let's kind of go through these real quick and talk about them. When we think of the physical layer, that physical layer is really how are you connected, right? So are you connected through fiber? Are you using wireless? Are you using Ethernet? Or coax, excuse me, and that's kind of going to be defining how is the physical connection being made from the device that needs to make the communication. Then we have what's called the data link layer, and at the data link layer, this is where we're going to be defining what's called frames, or how the packets are going to be kind of created and placed onto those wires or those wireless networks that we were just mentioning, and the method that they're going to be structured together. And then we get into, and a lot of times what will happen, and by the way, we kind of mentioned that this was done in 1977. Well, actually, in 1980, actually it was in February. So let's make a note of this here, and I'll make this a little smaller because I don't want to take up so much space. But in February of 1980, Project 802 created what's called the LLC in the media access control, or the LLC layer and the media access control were actually 2 sub-layers of this data link layer. So they called this Project 802. It's kind of unique that it happened in February of 1980, but a lot of times you'll hear the term 802.3, 802.11, and it's defining how these frames are going to be structured, right? So is it an Ethernet frame? What kind of frame is it, right? And so that's that's where that methodology comes from. Also, you'll hear MAC address. You'll hear that term quite a bit. That's the address that's physically a lot of times burned into the device. It's the physical address of the device that we're talking about, and it's actually specific to that device's hardware based on the manufacturer that created it. Like 3Com has certain address spaces and so on and so forth. So anyway, that's the MAC address. Then we get into, so again, a lot of times we'll call this the physical layer, the physical address, even though it's at the data link layer. At the network layer, this is where a lot of times we create the logical declaration, right? We're logically declaring that we want to have a particular IP address or a range of addresses. And so let's kind of think about how that works. And so if you think of an IP address, if you just went out to your command prompt and typed in ipconfig, for instance, on a Windows machine, /all, you're going to get an IP address, and let's say it's 10.1.3.65, and let's say you have a subnet mask And let's say that subnet mask is 255.255.255.0. And then let's say that you have a default gateway. And let's say that that's 10.1.3.1. And so that's pretty standard, right? This is kind of what you're used to seeing as far as how we might address an IP address. But when we look at this and we see this 10.1.3.0, and then we look at this piece here, we actually know that there's a unique relationship that's going on here. And it's important that we kind of understand that relationship. So it's actually kind of the byte that's being represented in decimal format. And so this is a 4-byte address or a 32-bit address. And that's what's being represented here, right? And then if anything's not in that address range, then we have to go outside of that address range in order to find what we're looking for. So a lot of times, you can equate this, this subnet mask is almost like defining a zip code in your local address range for your house or wherever it is that you live. Your zip code kind of tells you, okay, well, he's in the same zip code as me, so we're local. And so that's kind of what's happening with that subnet mask and the IP address. So let's dig into that a little bit further. And by the way, this again is all kind of going back to this network layer, and we're going to talk about the transport session, presentation, and application a little bit in just a second. But until we get there, what we want to do is we're going to go ahead and take a look at how does this IP address break down to decimal, and then also how does it break down to binary. And so let's go back to think about maybe the first time that we ever could count, right? And we would count, maybe we were playing a game with our friends or our cousin or something, our brother or sister, and we would count and we'd say, okay, when we get to 10, you win, right? And so we would learn that each one of those little hash marks there represented a point, or represented that you achieved the goal of whatever the task was. And so in this case, we were using what we would call base 1, right? Or unary to represent something, right? Every time we had a hash, it represented one thing. If it wasn't there, it did not represent something. It just only represented something if it was there. And so that's unary, or that's when we call base 1 in computing. That's kind of how we represent stuff. Well, if we take this and we want to expand this out, and we want to say we want to have, instead of just one value in that spot, maybe we have 2 values, a value that can represent an on state and an off state. And maybe we don't represent that in just one switch. Maybe we use multiple switches in order to represent these states. And so this can be done through 8 bits, 1, 2, 3, 4, 5, 6, 7, 8, right? And so I can have these 8 bits in a state where they're either turned on or turned off. And by taking and representing my data in such a manner, this gives me the opportunity to have a different type of representation. Now I have base 2 or binary. Each one of the bits can be in an off or on state and then represent something. Okay, and that's how we use computing, right? And that's how we deal with computing. We have magnets and we have lights and we have things that represent a switch or the state of something, right? And so that's how we do that. So when you think of Morse code, the do, those represented, those numbers were very binary. And so when we think of binary, instead of being base 1, now we have 2 values that can be available, or it is binary, right? Binary, bi meaning 2. So we have 2 values that are available here in binary. We're using base 2 to represent state. And if we look at the values that can be represented here, the first value has a value of 1 if it's turned on. The second one has a value of 2, 4, 8, 16, 32, 64, and 128. And so when I take the sum of all of these and I add all of those up, I get to 55. So when we look at a default a subnet mask and we see 255.255.255, Well, we know that that's just a byte, right? And when we say a byte, it means that it's 8 bits that have been put together to represent something that could be represented with those 8 bits and their state. And so that's what we see with a byte. So when we have a 32-bit address in IP version 4, this is what we see quite often, right? We see just this very scenario. And so that's what we see here, is we have that ability to kind of define that this particular portion of our address is used in order to identify what is local and what is not, right? Because when I come up here and I see 10.1.3, all those bits are turned on. Well, that's just telling me that that's the portion of the IP address that's used to kind of recognize what's local, right? The network. That's the network that's local to this IP address. That's its local address range. And then anything outside of that, it needs to reference something else. And so that something else in this case is what's called a default gateway. It's your router. It's how you're getting out. And so a lot of times that might be your router from AT&T. Well, AT&T gave you one real IP address, and that router then performs network address translation services, or it translates that one real address that's a 3 or a 16 or a 27 or whatever address range it is that your support provider provides to you. And then internally inside your house, you're using 10 or 192.168 or 172 or something like that, which is conforming to what's called RFC 1918. And so what happened was RFC 1918 basically stated that there was certain address ranges, 10, 192.168, and stuff like that, and 172 I think is another one. But these addresses are never going to be used. It's never going to be an address that's really out there on the internet. So much like your device that you have at home, it's going to allow you to use these address ranges to identify your refrigerator and your laptop and your alarm clock and Alexa and whatever it is that you're using inside your network. And then externally, there's just one address, and then it's doing NAT services, network address translation services, or translating the requests as they come in to your network. It won't allow. The neat thing about NAT is based on the protocol spec, is it won't allow the instantiation of traffic, right? So it won't allow somebody from the internet to initiate a connection through that endpoint into your refrigerator or whatever, unless the refrigerator called it, right? So in essence, it's kind of discriminatory in the types of traffic that it allows to pass through it. It will only allow traffic in unless it was requested from one of the resources that are inside. So it won't allow instantiation of traffic in, if that makes sense. Okay, so that's that, and so that's what we see there with the RFC 1918. In essence, again, we're just creating an address space that we can use internally that won't conflict with something that is real or external out on the internet. Okay, so now that we understand the basics of binary, and we understand kind of how an address works, when we look at an address, a lot of times you'll see an address denoted as what's called a classless inter-domain routing range, or a CIDR range. And so it'll say something like this: my address is 10.1.3.0/24. Well, what the heck is that? Well, it's the same thing that we just looked at up there. It's just saying that I'm using 24 bits, 8 plus 8 plus 8, 24. I'm using 24 bits to define my subnet mask, and anything else is inside my network. So this is the address that defines my network, and then any IP address, such as 65 or whatever, would be considered local. Anything outside of that address, so if it was 10.1.4, then that would be considered outside of that range, and it would need to go through a different device to get out. So it would need to go through that NAT device that we just talked about in order to get external from what's local. Just like your postmaster, if it's not in your zip code, then he sends it for out-of-town mail. It sends it to the router, right? Same concept. Okay. So now that we understand this concept here, this is one way that we represent state. is we take these objects that have the ability to represent multiple things, and then we roll that into an address. And that's what we have at level 3 of the OSI model, is we're defining what we call our IP address or our logical address range that then is used by the device that we're using, whether it be our phone or whatever. So depending on where you're at, you're going to have an IP address that's associated with you when you're communicating, but then that IP address is dynamic and it kind of changes depending on what devices you're using for communication. And so that's more of a logical addressing. Okay, so now that we understand that concept, let's go ahead and kind of go back to the OSI model, and then we'll come back and look at data state representation. So the next thing that we see here is when we're dealing with TCP/IP, which is the standard protocol that we usually use for all communication on the internet these days, we've now defined our address, how we can logically find what it is that we're going to be communicating with on the internet, but we have to communicate using a certain transport mechanism. And that mechanism is going to come in the form of either the transmission control protocol or the user datagram protocol. Now let's talk about those a little bit. The transmission control protocol is transmission-oriented guaranteed packet delivery. That means that whatever you send, it's going to get there. Every packet, and it's going to get processed in the order that you sent it, usually speaking. And so when you want to make sure that everything that you send gets received, then you're probably going to build your stack so that it leverages TCP for sending and receiving data. But that means that you have all this overhead for accounting, right? The accounting of making sure that you get every packet as it's being sent, that overhead is something that you have to use as part of your protocol stack. And so therefore, you don't necessarily get the performance that you might get because you have to account for everything. And so the flip side of that would be the UDP protocol. That is not transmission oriented. It's connection oriented. It's connectionless, and it's best effort. Okay, so it just sends the packet, hopes you get it, but if you don't, big deal, right? So when we look at, for instance, like a product in AWS called Route 53, that's a great example of this. So for instance, Route 53 is responsible for routing DNS traffic. And if you know anything about DNS, it's just when you go to mywebsite.com, it resolves it to an IP address that's really exposed on the internet, a real IP address that we talked about earlier. And so what Route 53 does is it says, oh, okay, well, I'm going to go and look up that name, mywebsite.com, and I'm going to tell you what that IP address is. That's called DNS. It's Domain Name Services. And it listens on a UDP port, that server that's providing that service, it listens on a port 53. It listens on UDP port 53 whenever somebody says, hey, who is mywebsite.com, or who is, Expedia or Priceline or whatever, whenever you go to search for instance, travel reservations. So that's how those names get resolved. And so Route 53, as an example, is a cloud provider service in AWS that simply provides the methodology to resolve those host names to IP addresses for your computers. So, anyway, that's kind of pretty awesome, right? And that happens with all that additional accounting stuff. We don't need to have all that accounting stuff when you just say, hey, who is this name? We just need to just give you the name, right? So that's when we would use that user datagram protocol, which is connectionless best effort, but we don't have all that accounting, so we get better performance. You got more throughput, you can get better performance by removing all of the extra accounting and using it for performance purposes. So depending on the the workflows that you're dealing with, one of these may be more desirable. All right, so the next thing that you're going to see is what we call APIs and secured sockets and WinSockets, and this is where a lot of times you'll hear where we talk about what we call transport layer security, or TLS. We'll secure the endpoint at that layer. Sessions layer, we secure the session with an SSL socket or something along those lines, or TLS. And so a certificate. And so what we're doing is we're just saying, hey, I have an X.509 certificate. I'm going to sign it, and I'm going to allow to terminate at this endpoint, and all traffic that will be sent across that endpoint will be encrypted. And so in order to understand that, we probably need to have a basic understanding of what a hash is so that we have a general understanding of encryption. So let's go out here and just kind of take a quick look at what's called the secure hash algorithm 256-bit. Now, in order to understand this algorithm, I need to probably talk a little bit more about this state representation thing that we were just talking about. So we've kind of already discovered what base 0 and base 1 and base 2 is. And then we also probably already understand decimal, right? So let's just talk about decimal for a second. But we know that decimal is 0 through 9, and that's representing the state, much like, 0 and 1 only represented 2 states. Now we have 10 states that are being represented, or dec, right? Dec means 10 decimal. So this is giving us base 10, right? So if we think about using decimal, a lot of times we just say, well, that's base 10 state representation as far as what can be seen in each one of those columns that we're representing whatever it means. And so that's what we usually use as humans to represent numerical values, but it doesn't have to be that way for computers, and it doesn't really have to be that way for us as humans. And so when we take that one step further, and that's what we did with hex, is hex allows you to say, hey, we're going to go 0 through 9, but then we're going to go A through F, right? So now, instead of having base 10, you have base 16, because you have 16 characters that have the ability to represent that same state, right? So when you're using base 16, you can represent a lot more information in a smaller amount of address space, right? Or smaller space. So with that, you'll hear about IP version 6. Well, remember that IP version 6, all addresses are public. There's no such thing. Remember what we talked about earlier with RFC 1918? Doesn't exist with IP version 6. All addresses are public because this is a 128-bit address. It's not a 32-bit address. So as you can see here, we have a lot more ability to represent state. But we're not doing a decimal with IP version 6. We're using a hexadecimal address whenever we use this to represent the IP version 6 address. So we use hex to represent whatever the IP6 address is, but all addresses are public. And so a lot of times, especially if you're using AWS, you have to still get that private functionality where you don't want anybody getting in like you would get with a NAT service. So that's where you would use like an egress only gateway or something like that within the AWS type of environment. But anyway, that's kind of where that comes from. But if you're using IP version 6, and that's something you might run into if you're dealing with cloud services in AWS. So then let's talk about this a little bit further because that's just talking about IP addressing and representing what the address is for your machine that you're communicating with. So now we've done that, and we've done it with IP version 6. But let's go ahead and let's take this one step further, because a lot of times what we'll do is with cryptography, we need to represent a lot of things in a very small space. And so we'll actually take this one step further, and we'll say, instead of just going 0 through 9, because remember, 0 through 9 gives me 10, and then I can go A through Z instead of A through F, and that gives me 26. And then if I did this in caps and go A through Z, and I do that again, now I got 26 plus 26, so now I got 62. And then if I want to go ahead and let you do like pushes and pops onto my stack, so I want to give you the ability to do that with plus and minus, right, with low-level programming. So now the combination of all of those resources, right, so I've just given you all of those things to represent state, and all of that, what did that do? Well, that gave us base 64, right? So now I have 26 plus 26, 26 plus 26, 52 plus 10, 62 plus 2, 64, right? Base 64. So we probably heard that before, base 64. But the problem is, what's the problem? Well, I got zeros, I got ones, I got L's, I got I's. And that is a problem for humans. So if I want to remove that human ambiguity, and that's what we do a lot whenever we're dealing with encryption, is humans have to interpret this number, and they got to read it, and they got to look at it. If that's the case, if they're in your workload, then you got to probably change this from base 64 to something more applicable, and that's where I think it's base 57 actually, base 57. That's where base 57 comes from. Might be base 56. Anyway, base 57 or base 56 is one of the two, but that's where we just remove all that ambiguity. So zeros and O's means the same thing. L's, I's, ones, they all mean the same thing. Okay, so now that we understand that concept of so state representation using characters, we can say, okay, well, this number means something, right? So number 726 might mean laugh out loud when you're using Unicode or when you're using ASCII text. So this is how we kind of represent things when we're communicating. Okay, cool. So now that we understand these big numbers, let's now go back out here to this hashing concept that we were talking about. And so this is another one of those big numbers, right? I know this doesn't seem like a very big number because it's only so many characters long, but it's actually a 256-bit number, right? That's a really big number. And if that seems a little obscure to you, well, that number is big enough to give every grain of sand in the world its own address. It's a really big number, right? Imagine how big that number is now. If every grain of sand has its own address, you have a massive amount of address space that you can address, right? Every grain of sand, you can put something in each one of those grains of sand and define something, right? So that is an index. That's what we're doing. We're creating this huge index. Oops, sorry about that. We're creating this huge index of whatever was put in, right? So the SHA-256, whatever you put in here, it will generate an index using this algorithm, this secure hash algorithm that will give you a thumbprint, basically, a digital thumbprint of whatever you put in. So for instance, my name is Tommy Cooksey. So when I type in my name and it's all and it's got the uppercase T in the O and it's got the one space in the middle, this is the hash, this is the output of that. And when we use the SHA-256 hashing algorithm, two of the characteristics that we have of this is it's one way and it's collision resistant. One way in that I won't be able to take any other data and put it through this and get this same index. It's one way. This is the only index I will get with this input. And this input can vary. I can have up to 2 gigs of data or 10 gigs of data or however much data I want to put in through it, but it doesn't matter how much data I put through it or however much I vary it, that data, this is the index that I will get from that input, and it will only be this. So it's a very huge address space, right, that we're using. And then we're having this index in order to basically define that that's what it is. So that's the one-way concept. And then collision resistant, meaning that, or actually, that's the collision resistance. The one-way, meaning that I won't be able to take this and figure out what the input is. So I won't be able to take the hash and figure out what I put in as an input. That would, that wouldn't be capable. I won't be able to do that. So that's one way. Collision resistance, meaning what we were saying earlier. I can't put anything else in and get this same index out as a result. That would be a collision, and they're resistant against that. And so this hash algorithm is built this way. It's an algorithm that's built this way to create this ambiguity in this address space so that you can then use this for indexing and things like that. And we use this for building a lot of things like, creating PKI, public key infrastructure. We have asymmetrical keys and stuff like that. Well, an asymmetrical key is just a hash that is a private key. So we take this private key and we run this private key through and then we run it through again and remove all the ambiguity, all the O's and the L's and the B's and the it's called RIPE, something RIPE 53 or something like that. But we take that hashing algorithm and then we remove that, and then that gives us our public key, right? So the public key has the same derivative as the private key. The private key is the same derivative. But then when you sign something with the private key, you can use that derivative to find out that it came from the same thing, right? You can use mathematical operations to find that out. That's what we do when we sign transactions. That's how we know that it came from an individual, because they have their key. And we use this all the time, right? So this is private key is just a public key that's been hashed twice. That's it, right? Basically. And so now that we understand that, we'll use that a little bit in just a second. We'll put that in your back pocket for just a second. But to understand where this might come into play, think about this for a second. Why is this important? Why would you use this? Well, you've probably all heard your network administrator tell you that when you type in your password, it doesn't go across the wire. Well, how does it not go across the wire if I'm still able to log in when I type that password in? Well, what goes across the wire, is not the password. it takes the hash, right? And then maybe it takes that hash and runs that hash through another hashing algorithm. So it takes that out, puts that in, takes that out, puts that in, takes this out, puts this in. This is called the stretch, by the way. And maybe it does that a random number of times after you typed your password in. And then it takes the hash of the 7 times of stretch, or 78 times, or whatever that random number is, and it sends that across the wire. And then on the other side, it does the same thing, and if it matches, then they must have typed in the right password on the client side. So therefore, it lets them in. And so anyway, that's how a lot of times you can securely send a password across an unsecure medium, is using the stretch and then sending the hash of the input that was done on the password ingestion side. So anyway, so this is also used again whenever I want to take a private key to generate a public key. And so now we have a asymmetric set of keys, private key that's only available to me, public key is available to anybody, and there's a direct mathematical relationship, but I can't use the public key to figure out what the private key is. Holy cow, that makes sense, doesn't it? All right, cool. So now let's go back here and let's look at our diagram. And when we come back and we think of what's going on here, what we're able to do is we're able to sign transactions and then generate a secure communication session between two entities using that concept that I just talked about. So this is called PKI, or asymmetrical encryption. But I'll sign something, send it to you, you sign something, you send it to me, and then we just agree on a random number. That's it. And now we can communicate across an unsecure medium using that random number to encrypt all the data that's in our session, because I know who you are and you know who I am, and we both agree on the number, and we did that in a secured methodology in the handshake, and then we'll just rotate that session key on whatever the setting is that we define it for. But generally, that's basically how this works. Okay, so that's asymmetrical encryption. I want to kind of tie this up, and I probably need to talk a little bit about application level. So this is where you talk about like SSL and stuff like that when you're setting up that SSL connection or secure socket layer connection. And so by the way, too, real quick, sometimes people get really confused on this. I mean, here's a great analogy. If you're not familiar with what happened in World War II, during World War II, the shipping lanes of the English Channel were being sunk by German U-boats, and I think we're all familiar with that story. But one of the things that we used computing in order to combat that problem. And so at a place called Bletchley Park in England, there was a gentleman named Alan Turing, and Alan Turing is an amazing man. He was the first of all father of modern computing. He wrote a computing paper in 1937, I believe, that kind of describes how all computers work today, and we call them a Turing complete machine because they have the ability to do loops and for and while statements, and we can send code to it, and then it can go through that set of code and find out the problem. And so that's called Turing complete, and so it came from Mr. Alan Turing. But what happened was at Bletchley Park is they were using computers, they were using this methodology that I'm talking about here in order to find out what was happening whenever the Germans were sending radio transmissions to those U-boats in the English Channel and telling them what ships to target and things like that. Their communication methods were using a thing called the Enigma machine, and the way that Enigma machine was configured on both ends allowed them to encrypt the traffic in so much ambiguity that it was impossible for anybody that didn't know how to crack that code could understand what it was they were saying. And so they used a few different methods. One of those methods included computing and social engineering and a few other things. But they were able to crack it, and then they were able to kind of discover when some of those attacks were happening and take action. So in essence, if you're familiar with that story, that's basically the same thing that we do when we use secured sockets, when we use a VPN connection, whenever we talk about tunneling through the internet, we're able to establish that secure communication because we're relying on these cryptographic primitives that I just spoke of. Okay, so now that we understand that concept, the last thing that you'll find is the application layer, and this is really where the rubber meets the road. So this is where, you know, for instance, if I'm calling my cool website, if when I go to mycoolwebsite.com and you see slash, oh, well, I hit it through my device on my phone, and now I'm at the slash mobile all of a sudden when I look at the URL. Well, how does it know that? Well, it's just hitting that particular API endpoint and says, okay, we'll render this video for a mobile device through this baud rate or whatever. And so it sees that in basically in the header information when you're making the HTTP request. But it's all about, you know, how do I make this application work best for the user that is trying to consume it. So it's all about really what we call the UX, but it's basically trying to give the user the best experience. So there's different things that we can do in order to optimize our performance and maybe bring that information closer to the user so the user gets a better experience. And so anyway, that's kind of the 7 layers of the OSI model. In my next discussion, probably what I'm going to do is I'm going to expand this out and talk a little bit about how this is going to be used in conjunction with encryption and stuff like that, as well as with kind of industry storage and the way that we store data in the industry as far as back end, middle tier, front end, and how workflows kind of work and how really kind of how some of those workflows are getting disrupted with what's happening in today's day and age. If you want to find out more about me, you can go out and check me out on my LinkedIn page. Feel free to connect to me there. You can also find me through my various training offerings that I have available as well. So again, just feel free to ping me, and I'd be happy to talk with you about whatever it is that you're struggling with. All right, guys, have a great day, and I hope you enjoyed this video. Thanks.